Thevenin equivalent circuits. This topic, Thevenin equivalent circuit, implies that you can draw an equivalent circuit for any linear circuit. Consider a circuit which is linear and it contains some components such as resistors, voltage sources, current sources. They may be dependent sources. Okay. 2 points from that circuit, points A and B, are extracted. Thevenin method says you can design a simple circuit, and that circuit contains one resistor, one voltage source, and if you select proper values, let me say the voltage of this source is Thevenin voltage, and let me call Thevenin resistance. If you select proper resistor and proper voltage source, this simple resistor will be equal to that huge circuit. Okay, that the circuit contains lots of components. This is a circuit. This is the Thevenin equivalent model of that circuit. A prime and let me say B prime. Okay, they will be equivalent. You can replace this huge circuit with its Thevenin model. Okay, but what you do is to select proper values, the Thevenin voltage and Thevenin resistance. How to calculate the Thevenin voltage and Thevenin resistance? Consider a circuit and its components are linear. Okay, that's important. It should contain linear components. The number is not important. The number can be low or high, and it can contain sources. Actually, if you draw the graphic of sources, they will be lines. Okay, so linear components and sources have graphics like that. If you draw the graphics, they should be always lines. Okay, resistors have a graphic like that. Okay, it passes through the origin and it has a slope, and a voltage source is like that. Sorry, a current source. This is a graphic of resistor. This is a current source. Its current is fixed. Voltage can be anything. This is the graphic of a voltage source. Okay, so the components should have a graphic of lines. For example, let me give another example. Look. This is a graphic of diodes. Okay, another components. Diodes. So diodes is not linear. Okay, if there is a diode in your circuit, you cannot find a Thevenin equivalent for that circuit. Okay, so from that circuit you look at two cables and you calculate the voltage, open circuit voltage, open circuit. Okay, you take 2 points, you measure the voltage. that voltage is the thevenin voltage. That's it. Okay. And then you have to calculate the thevenin resistance too. You will look at the resistance between these two cables, but you have to turn the sources off. Turn the sources off. Okay, when looking at the resistance. So you have to do voltages. Volts will be 0 volt. Current source will be 0 amp, and then you measure the resistance. Why do we need Thevenin equivalent models? Okay, where are they used? Consider you have a circuit. You have a complicated circuit. Okay. In that circuit, there is a component here. Let me not define the component. There is a component. You investigate the proper component. Okay. You always change this component X. Okay. You change X. You put another component and analyze the circuit. If it's not okay, you will change another component. You will put another component. So if you replace a component, you have to make the circuit analysis completely from the beginning. Instead, this circuit is connected 2 points. This component is connected 2 points of that circuit. Okay, this is a linear circuit. Instead, you reject that component. Okay, reject. This is the circuit. You reject that component and you find the Thevenin equivalent of that. This is point A, this is point B. Thevenin equivalent of points A, B. It means you will find a Thevenin voltage. You will define a Thevenin resistance, A prime, B prime. Thevenin voltage, Thevenin resistance. Instead of analyzing the huge circuit, big circuit completely, okay, first you calculate the Thevenin equivalent of that circuit, and then put X here. Okay. So instead of changing a component in a big circuit, if you change a component in a big circuit, you will make the analysis from the beginning. It will be difficult because it's a big circuit. It has lots of nodes, lots of branches, loops. Okay, you will have many equations to analyze that circuit. But in the equivalent circuits, when you want to change these components, okay, you will reject it, put another component. If it's not okay, reject it, put another component. And here you will analyze a circuit which contains 3 components. Okay, so analysis of that circuit is much easier than the original circuits. Analysis of the Thevenin equivalent circuit is many times much easier than the original circuits. Okay, and for sensors, okay, sensors in real life, sensors are many times modeled as a Thevenin equivalent. Okay, for example, a microphone is defined as a Thevenin equivalent model. Okay, a microphone, a temperature sensor. Okay. So it's important to understand the Thevenin equivalent circuits. Let me show the Thevenin application on a circuit. consider this circuit. Or let me change this. Okay, I want to find the voltage of source 2. Okay, this is I source 2, that's a current source. V source 1 is a voltage source, R1, R2, R3. Okay, I want to find the voltage source, voltage of source 2. That's a current source. Its current is given, but I don't know the voltage. And let me apply the thevenin technique on the circuit and then analyze to find Vs2 value. Okay, so thevenin equivalent means replace the circuit with thevenin equivalent, with thevenin circuit. What do I mean? Thevenin circuit is a voltage source and a resistor. Okay, this is called a thevenin circuit. So I want to find the value, this value voltage. It's the voltage between points A and B. Okay, points A and B. So I have to calculate two values, thevenin voltage and thevenin resistance. V source 2 is the voltage of the current source. So while calculating the thevenin equivalent of the circuit, I have to extract current source 2. Okay, I will not use current source 2. So this is my circuit. I reject this component. Okay, I reject that component. I will find a thevenin equivalent for that. A prime, B prime. Thevenin voltage, thevenin resistance. Then I will insert the current source here and analyze to find V source 2 value. Okay, so after finding the thevenin equivalent, after defining the thevenin equivalent model, instead of analyzing that circuit, this circuit, I will analyze a smaller circuit. Okay, let's calculate the values of this circuit. What's the thevenin voltage and thevenin resistance of this circuit? The open circuit voltage. Okay, you don't connect anything. You directly calculate the voltage of the points. That's the thevenin voltage. Okay, what's the current on this resistor? 0, because there is no component connected. So voltage of this point will be equal to A, because there is no current on the resistor. This point is equal to B, because they are connected with a cable. R3 doesn't have any effect on the circuits, okay, because it's open circuit. There is a voltage. That voltage is divided on two resistors. There is a voltage division, and the voltage of R2, okay, this voltage is equal to open circuit voltage, VAB. Okay, so V2 is the voltage of this resistor, is equal to open circuit voltage, which means the thevenin voltage, is total voltage, I apply the voltage division rule, times the resistor, okay, the resistor of this voltage, divided by, can you remember? The total resistance. Okay. Voltage of a resistor is equal to total voltage times that resistance divided by total resistance if they are connected in series. Now they are connected in series because R3 have no effect. R3 has no effect. Okay. So that's the open circuit voltage, thevenin voltage. Similarly, I have to calculate the thevenin resistance. What's the resistance of the circuit? While calculating thevenin resistance, while calculating our thevenin, turn all independent sources off. Okay. So if you turn the sources off, what does it mean? What does turning a voltage source off mean? If you turn off a voltage source, has 0 volts. Okay, so it's like a short circuit because it has 0 volt too. Turning off a current source is 0 amp current. It behaves like an open circuit. Open circuit has 0 current always. So let's copy the circuits and redraw turning the sources off. There is a voltage source only. I'm replacing it with a short circuit. So what's the total resistance between points A and B? How are these connected? You are looking from A and B. It's very important. Okay, the resistance between A and B. R1 and R2 are connected in parallel. Okay, because one terminals are connected here, the other terminals are connected on that point. So R1 is parallel R2. And if you combine and redraw the circuits, this is R3. This is R1 parallel R2, point A, point B. Now, what's the total resistance? They are connected in series now. Okay, parallel. Here they are connected in series. So the total resistance between point A and B is R3 plus R1 parallel R2. Okay, so I have calculated the total resistance. So thevenin equivalent model is this is R thevenin. What's the value? Value is this. Okay. What's the thevenin voltage? What was it? It is this. Now, these are points A prime and B prime. I have calculated the thevenin equivalent of my circuits. Now I will put the current source here. I will put here. I know that this thevenin equivalent circuit behaves like the actual circuits. Okay, so what's the voltage on the current source? Now it's very easy. Why? Because I know the voltage of this component. This is a resistor. I know the current of that resistor. So what's the voltage of this circuit? This resistor, sorry. What's the voltage? For example, let me say this is Vx. What's Vx? Vx is R times I. What's the resistance? R3 plus R1 parallel R2. What's the current on it? The current voltage of a resistor is resistance times the current entering from positive. What's the current in that direction? The current in that direction is minus IS2. Minus IS2. Okay, because this is a current source, it's flowing like that from right to left. Okay, so this is the Vx. If you apply a KVL, look. Okay, so if you apply a KVL, start from here. There is a voltage increase of Vs1 times R2, R1 plus R2. Okay, there is a voltage drop of Vx minus Vx, and there is a voltage drop of V source 2, and the same point summation is 0. So Vs2 is equal to sorry, this should be plus. Okay, there is a voltage increase, it should be plus. So Vs2 is Vs1 R2 divided by R1 plus R2 minus Vx. Vx, what's Vx? Vx is this. Minus Vx. Okay, that's it. We have calculated Vs2. Now, let's have a numeric example. Let me use some values of the circuits. Question. Find a Thevenin equivalent model for points A, B. Okay. I want you to draw a Thevenin circuit. You can name as A prime, B prime. Okay. It means I want you to draw a equivalent circuit. For example, any components. If you connect a component X here, okay, and then you reject that component. You reject that component. And connect here. The component X cannot understand that it's connected to another, a different circuit. Okay, I want you to do this. Or, for example, if you connect another component, for example, component Y, okay, that component Y, when you replace the circuit, okay, when you do this, component Y cannot understand that there had been a change. Okay, there shouldn't be any change in voltage of component Y, current of component Y, power of component Y. Okay, if you put if you replace the components between these two circuits, there shouldn't be any difference of these values. So let's calculate This is component Y. This is my circuit, and I need to calculate two values. One, thevenin voltage. Thevenin voltage is the voltage between points A and B. Okay, what's that voltage? I can calculate that voltage applying a KVL. What's the voltage of current source? It's equal to VAB. Okay, actually VAB is the voltage of current source. So I can calculate the voltage of VAB like that. There is a voltage increase here. Let's write the KVL rule. Start from here. Voltage increase of 5 volts. Continue. There is a voltage drop minus 10 times current. What's the current? Is it 15 or minus 15? Yes, minus 15. Then I continue. There is a voltage drop of VAB. Plus minus VAB. Okay. So from here, I have reached the same point. Summation is 0. VAB is what? 5 minus. So it's minus 145. Sorry? Yes. Minus times minus will be plus. Volts. Okay? This much of volts. And we know that it's the thevenin voltage. Now, let's calculate the thevenin resistance of the circuit. While calculating the thevenin resistance, what should we do? Turn off sources. So I should do this: 0 volts, 0 amp, and then look at the resistance. Okay, 0 volt means a cable. 0 current means an open circuit. So what's the resistance between points A and B? What's the resistance? Resistance. There is only one resistance, that's 10 ohms. Okay, so I have calculated the thevenin voltage minus 155, thevenin resistance 10 ohm. So the equivalent circuit is like that. That's A prime, B prime, minus 155 and 10 ohm. Okay, this circuit behaves, if you look at the points A prime, B prime, and if you look at the A and B of this circuit, you cannot understand any difference. If you measure the voltage with a multimeter, you will see same values. If you connect a resistor, the voltage of the resistors, okay, will be same. Okay, these two circuits are equivalent if you look at only points A prime, B prime, and AB. Sorry, I made a mistake here. In this calculation, VAB is transferred to this side, and what remains on that side is positive 155 volts. So let me change the values. This is positive 155 volts.